This program is brought to you by Stanford University. Please visit us at stanford.edu.
We talked a little bit about curvature last time. Curvature, these are hard concepts. They're not easy, and partly they require, in order to do them in an elegant way, requires a degree of notation that's a little bit sophisticated. I told you what the answer for that, I told you what the curvature is. You go around a little closed loop, and a vector doesn't quite come back to itself, and that's an indication of curvature. I wrote a formula on the blackboard. I thought today I would actually derive that formula, but to do it in anything like a reasonable amount of blackboard space and a reasonable amount of time, it's very, very useful to introduce some, I don't know if the word is notation or conventions or mathematical ideas that are not very hard. And in fact, they're ideas that if you've followed the development of either my or anybody else's quantum mechanics course, you'll be extremely familiar with. So I will use those ideas to derive the curvature. The curvature, as I think somebody pointed out, it was probably Michael. You're here, aren't you, Michael? Michael, yes. I think you pointed out that it's a commutator. So I think we will go through that and show you the fast way to derive the curvature. But as I said, it's slightly abstract. So we have to go through a couple of abstract definitions. The basic idea is the idea of an operator, a linear operator, operating on a vector space. But the vector space could be a space of functions. We see that all the time in quantum mechanics, where, for example, the idea of a derivative is a linear operator that operates on functions. So there's an example. Another example of linear operators are matrices that act on vectors. But in fact, we can combine the two. Supposing we have a function which is a vector, well, which, let's not call it a vector in a function space, that will confuse us too much. Let's just call it a function. Supposing we have a function, but not a single function, a collection of functions which correspond to the components of a vector field in space. All right, so depending on the dimensionality of space, if we're talking about four-dimensional space-time, that would basically be four functions of space, and what would we call them? We might call them V alpha of x. All right, so I've already mentioned that one kind of operator, an operator is of course an operation that you can do on a function to get another function, but a linear operator is a particular kind of operation of which, for example, a derivative with respect to any of the components of x, derivative with respect to x mu, that's an operation that can be applied to V alpha of x, and therefore we call it an operator. That's one kind of operator that we can have, a derivative operator. Let's make a list of some operators over here. First of all, this by no means exhausts all possible operators, just a couple of examples. The derivative with respect to any of the coordinates, that's a linear operator, and it can act on any kind of function. The function could be a scalar, it could be a vector. If it's a vector, then of course it corresponds to differentiating all four components of the vector. So if we apply this operator, or allow it to act on V alpha, all it really means is the derivative of V alpha of x with respect to x mu. That's all it means. Okay? Hit the object with the operator and just do it. All right, so derivative with respect to x is a operator. Another kind of operator doesn't differentiate. It might just multiply a function by another function. So just multiplication by any function of x, take any function of x and use it to multiply your starting function. That's another operator that you can do. So for example, applying f of x as an operator to v alpha of x just gives you, I needn't write it over again, but I will. It just gives you f of x, let's create times v alpha of x. The little dot is redundant, but I just want to distinguish between f of x as an operator acting on v alpha of x. All it does is multiply. Okay, so that's another example of an operator. But yet a third kind of operator that we can do on v alpha of x is just to multiply it by a numerical matrix. Remember, this v alpha of x has components. It forms a column vector in a space. For this purpose, just think of x as fixed. All right, now just think of x as a fixed position, and we can multiply v alpha of x by a matrix. Sorry, m on v. Let's see what that means. M applied to the vector v means I would like to get the alphth component of it. Well, the rule for that is m alpha beta. Those are the matrix entries of m, multiplying v beta and summing over beta. That gives you a vector with a component alpha, and it is a linear operation applied to a vector. So there are three examples. One of them is just multiplication by a numerical matrix. Another is differentiation. Another is multiplying by a function of x. We can even get fancier. We can take matrices, alpha, beta, which themselves depend on position, and multiply by v beta of x. I'm not going to write that this is equal to what I've already written. So we can have an operator which is both a matrix and a function of x. We can even do more complicated things than that, but I think you get the point. Now, the covariant derivative, the ordinary derivative of a vector, is an operator applied to the vector. But the covariant derivative is also an operator applied to a vector. It's a more interesting one in many respects, but let me just point that out and explain to you exactly in what sense the covariant derivative is an operator applied to a vector field. All right, we write it del m. That's the notation for covariant derivative, or del mu. I guess I'm using indices mu and nu and alpha and beta. This means the covariant derivative with respect to the coordinate x mu. So it's like d by dx mu applied to a vector with components v alpha is, by definition or by construction, the derivative of v alpha of x with respect to x mu plus, now, gamma, I'm just writing the usual expression for covariant derivative, an index down here, which, don't think of that as being a matrix index. I'm going to take the matrix indices and write them in red. But remember that the Christoffel symbol has three indices, alpha and beta. Now, the way I want you to think about this is for each mu, there's a matrix gamma sub mu with indices alpha and beta. So I've reddened the matrix indices. Of course, it is really just gamma mu alpha beta. But I want you to keep in your head, I want you to imagine that gamma mu alpha beta is a set of 4 matrices. Alpha and beta are the matrix entries, and mu just tells you which of the 4 matrices you're talking about. And now you multiply that by V beta. Let's use red to indicate the matrix indices here. And sum over beta. Notice that that's exactly what we did over here, except there are 4 such operations, 1 for each direction mu. All right, so the covariant derivative is a combination of differential operator, derivative operator, and matrix multiplication. Now, gamma mu is not just a numerical matrix. Typically, it's a numerical matrix that depends on position, so it's exactly like this kind of thing over here. All right, we could summarize it by the notation delta mu equals derivative with respect to x mu plus gamma mu. Now, that looks stupid. What does that mean? What it means is exactly what I wrote up here. When it applies to a vector, you differentiate the vector, and then you add to it the matrix gamma mu applied to the vector. This gamma mu here is a set of 4 matrices. It's exactly this set of 4 matrices over here, but I've just called it gamma mu, and you keep in mind that there are really 2 hidden indices here, which are acting as matrix indices which act on the vector. So that's a little notational device which summarizes what's written up here, but when you act on a vector to find out what del mu does, it does exactly what's written here. Right. So that's a nice, and remember now that gamma mu is a function of x. But it also has the 2 hidden indices there.
Are the 4 matrices time in 3 special coordinates?
Say it again?
The 4 indices of the time in the 3 special coordinates, so we're limiting it to 4 space.
Yeah, the moment with, right, I'm talking about 4 space. Yes, absolutely. If we were talking about some other space with different dimension, right, yeah, that's right, exactly. Okay, so that's something to keep in mind. It's a little notational device that we will use. Now I want to show you that in the process of going around a small closed loop and asking how something changes when you come back to the origin, in effect, you're calculating a commutator of 2 operators. Oh, before I do it, perhaps we should just discuss very quickly the commutator, the idea of a commutator. You mostly know what it is, but I'll tell you what it is. If I have 2 operators, let's call them A and B, whatever they are, they could have derivatives in them, they might be multiplication by matrices, they might be multiplication by matrix functions of position, they might be sums or differences of such things, A and B. The product, what does the product AB mean? Well, it means you first act with B on whatever your operations are supposed to act on. For example, if it's supposed to act on a vector, act on a vector. The result of acting with B is a new function, and then you act with A on it. So first act with B and then follow it by A, and that of course defines the product AB. The difference of AB and BA is of course called the commutator of A with B. There's only one little identity that I want to prove and that we'll use, and it's the following: that the commutator of a derivative, let's say the derivative with respect to x, any particular x, doesn't matter, the commutator of the derivative of x with respect, and a function of x is equal to, and I'll tell you exactly what this means in a moment, df by dx. Now, I may or may not have the sign right, but we'll work it out. What does this mean? F of x now is just a numerical function, and not a numerical function, a function, but it's thought of as an operator. It's not the thing that these expressions act on. The things that they act on, we can give another name, we'll just call v of x. Right? It doesn't have to be a vector function of x, just some function of x. Let's see what this says. Let's see what the meaning of this is. First of all, the first term is d by dx f of x. That's one term here. And the other term is minus f of x d by dx. Now, what's the difference between these two? Well, it's hard to say what the difference between these two are until I tell you what they do. What they do is they act on functions of x. Let's say v of x. V of x. Now, what's the meaning of this? This means first multiply by f. By the time you've multiplied by f, you have a new object in red, and then differentiate the whole thing. That is the operation of first multiplying by f and then differentiating. And it constitutes the instruction that's associated with the product f times d by dx. Over here, we first differentiate with respect to x and then multiply by f. Okay? Let's see what the difference is. What is this dx of f times v of x? For this, we just use the product formula, that the derivative of a product is the derivative of f with respect to x times v plus f times the derivative of v with respect to x. All I've used is the simple calculus rule that the derivative of a product is the sums of, well, you know what. Then we have to subtract off minus f dv by dx. But that's the same as this. So these cancel. And what are we left with? We're left with the instruction that when you apply the commutator of d by dx and f, this is, of course, the commutator of derivative with respect to x and f on v, you get exactly the same thing as just multiplying v by df by dx. After all of this whole operation, including all these derivatives, the entire instruction is to multiply v by the function df by dx. So that's why we write that commutator of the derivative and the multiplication by a function of x is just df by dx. And what does it mean? It means when you apply this to some v, it gives you the same thing as just multiplying by df by dx. All right, so that's as tough as the mathematics is going to get tonight, I think. The idea of a commutator and the idea of a covariant derivative as a operator. Okay. Keep this in mind. We need a basic little theorem that I'll just write it out in longhand. D by dx times f of x minus f of x times d by dx is the same thing as df by dx. Try it on any function. Take any function and apply the rule here, subtract them, and it's the same as multiplying by df by dx. So we'll need that. Okay, next. I guess we can use this one here. Let's take a little rectangle. I won't try to be too general right now. I'll say let's pick two directions in space or in space-time. One direction and take a little differential distance that I'll call dx mu. And now take another little differential distance. Let's think of it as oriented. Dx mu, a little infinitely small displacement. Think of it as displacement. All right. And now take another displacement. I'll tell you what, let me even simplify it more. Let me simplify it more. We're going to take two displacements. No, it's simple enough. dx mu this way, and another one, delta x nu this way. These are two vectors. I've just indicated them with indices mu and nu, but it's not important what the mu and nu are. These are just two distinct vectors, infinitely small, both of them. And they simply pick out a pair of little elements of a tiny rectangle in space, or in space-time. Right? What we're going to do is we're going to parallelly transport something around the rectangle determined by these two vectors. Now, let's imagine that as we transport the object around these vectors, we're going to start at position A, we're going to go to B, then we're going to go to C, we're going to go to D, and then we're going to come back to A. We're going to go right around that loop in space. But what happens to the thing that we're transporting around is that it won't come back to exactly itself. Why? Because there's curvature. We've seen how on the surface of a sphere or on the surface of a cone, how when you go around a closed loop, you don't come back to yourself. So I'm going to draw next to it over here what happens to the object. The object starts at some value which we can call v, and let's think of it as a vector, v sub a. I won't draw it, we'll just say it starts at a point VA. We transport it over to here, and it becomes VB. We transport it over to here, and it becomes VC. And then we transport it over to here, it becomes VD. But then when we transport it back along the last leg, it doesn't quite come back to itself if there's curvature in there. And so let's just call the result VA prime. Let's just call it VA prime. And we're interested in the difference between VA and VA prime. So let me show you a little identity, and then we'll interpret that identity in terms of covariant derivatives. We're imagining, incidentally, parallelly transporting these vectors. And it's the effect of curvature that makes the vector not quite come back to itself. All right, so I'll just represent that by saying we go around in a little closed loop, and we fail to come back to the starting point exactly. Not in space, but in the direction of the vector, yeah.
Question, the difficulty of it not matching is it doesn't come back to the same point, or that
it comes back to the same point, but comes back oriented differently. Okay. So I'm just representing that by a little mismatch here. I don't know how else, right. So let me take the following identity. All right, let's take VC minus VB, okay? VC minus VB, that's going to be related to some derivative of V along this direction here later on. But for the moment, it's just VC minus VB minus VD minus, well, no, I'm sorry, I didn't do this right. I should have started differently. Let me just find my notes here. Yeah, I'm sorry. VC minus VD. That's the difference between the vector here and here, and it's clearly related to some derivative of the vector along the direction dx mu here, along this direction, which is dx mu. But let's just call it vc minus vd for the moment. And now subtract from that minus vb minus va. Okay, so let's see what I've done. I've taken vc minus vd, that's a little difference here, and subtracted the corresponding difference down here. I've taken a difference up here and subtracted the corresponding same thing except displaced down here. That's going to be related to a second derivative. It's a difference of differences, vc minus vd minus vb minus va. That's the thing that makes up a second derivative when we do it with calculus. Difference of differences. All right, that's one thing. Now I'm going to write a similar thing. I'm going to subtract from it. Let's put this in brackets. And I'm going to subtract from the whole thing a very similar expression. Notice what I did here. I took a difference going horizontally and then took the difference of differences moving vertically. Now I'm going to do it the opposite way. I'm going to take the difference vertically and subtract off when I move horizontally. In one case, I took a derivative this way and then differentiated it vertically. Now I'm going to take a vertical derivative or vertical difference and displace it horizontally. So let's see, what am I saying? I'm going to subtract vc minus vb, vc minus vb, and then from that subtract the same kind of thing over at this end, except vd minus va prime. Instead of coming back to here, we know we come back to va prime, so I'm just going to subtract vd minus va prime. That's related to two different orders that we can take differences. Straighten that out.
Why did you choose to subtract the B minus and C from D to A instead of the other way around?
Wait, sorry, which way?
Why don't we use the first term, VC minus VD,
Yeah.
and then do minus VD minus VA? Why don't you do it the other way around?
The VC minus VD
No, the
minus
first one's
VBI minus VA.
fine. On the second term,
Okay.
why did you choose to do VC minus VB minus VD minus VA instead of the other way around?
What other way around?
VD minus VA minus VC minus VB. So why
Because
did
I
you
know what I want to get. Because I know what I want to get. I know the answer that I want to get. My point is, well, you'll see in a moment. This has been engineered to give me a particular answer. It's been engineered on purpose to give me a particular answer.
Because you're going around counterclockwise.
Yeah.
If you switch it, you put a plus in.
What's that? I can define anything I want. I'm a free man. I can do anything I want. I choose to define this, okay? Now, having chose this,
Final minus initial.
yeah.
dx mu and
Yeah.
dx.
Yeah. If we think of going this way as the positive axis and this way as going the positive axis, I've always subtracted the more positive from the less positive point. But the point here is I've engineered something to give me an answer I want. Let's see what the answer is. Notice that VC cancels. There's a plus VC here and a minus VC here. Okay? There's a minus VD here, but a plus VD here. Two minuses make a plus. Okay? How about VB? Incidentally, upper and lowercase b are the same thing. There's a minus VB here and a plus VB here. So, many things have been engineered on purpose to cancel out. VC cancels out here and here. VD cancels out. Minus, plus. VB cancels out. Minus, plus. And the only thing that's left over is VA prime minus VA. Okay? VA prime minus VA equals You're right. VA, no. Yes, you're right. VA minus VA prime. No, I think I got it right. There's two minus signs here. So it's plus VA, and there's three minus signs here. So, good. VA minus VA prime. In other words, I have succeeded in writing the difference of VA prime and VA in terms of various derivatives. They're not yet derivatives, of course. We're going to turn them into derivatives in a minute by making these distances infinitely small. But we've actually written the difference in terms of a derivative of derivatives. In other words, a second derivative. Now let's see what that second derivative is. Let's take the first expression up on top. First of all, let's take VC minus VD. VC minus VD is related to the derivative of V with respect to x mu times dx mu. The derivative, the V here minus V here, is the change in V when you change x mu a little bit times the change in x. So that's the first term up here. Now what's the second term? The second term is exactly the same thing, except displaced downward. Both of these, VC minus VD and VB minus VA, VC minus VD and VB minus VA, are both related to derivatives along the axis dx mu. All right? But what's the difference between them? The difference between them is a derivative of this with respect to the vertical axis. It's the difference of differences. And so the actual full thing that's written here for infinitely small, for infinitesimal elements, is we differentiate this, again, dV. It's actually, excuse me, I'm not writing it correctly. This should be covariant derivative because we're parallelly transporting. Because we're not just doing ordinary derivatives, we're parallelly transporting and taking the covariant derivative, the covariant difference between these. So the covariant difference between these is covariant derivative of V times dx mu. And then if we want to subtract off the second half of it here, we simply have to multiply it by, we have to do another derivative, del with respect to x nu, and then which way is it? It is dx mu delta x nu. That's what appears here, the derivatives, or the difference of differences. The difference when you transport along the dx axis, and then take the difference of that when you transport the whole thing along the delta x-axis. Okay, so that's what this is. What about the other term, the second term that we subtracted off here? It's exactly the same thing, except in the opposite order, where instead of, well, let's just look at it. What's the first thing here? We're subtracting. This is VC minus VB. VC minus VB is the derivative with respect to the vertical axis. So that's del nu V times delta x nu, oops, times, let me get it right, yes, times delta x nu, and then d mu times dx mu. In other words, the difference between these is just the order in which I differentiate. If I can differentiate in the horizontal direction, or I can differentiate in the vertical direction. Covariant derivatives, the difference between those two derivatives constitutes what I've written here. Okay. So what have we found? we found that the change in v when you go around a closed loop, first of all, contains these little differential elements, the x mu and delta x nu. That's the little area element. That's the little area element contained in the rectangle. Rectangle or parallelogram. It doesn't have to be a rectangle, it could be a parallelogram. And then it contains delta nu, delta mu, v minus delta mu, delta nu, v. What is that? That's the commutator of delta nu with delta mu on v. The first term, delta nu is to the left, delta mu is to the right. In the second term, delta mu is to the left, delta nu to the right. So here's a fancy expression involving the commutator of two covariant derivatives. The commutator of two covariant derivatives. Each one is itself an operator. When you commute them, you get another operator. When you apply that commutator to the original vector, starting vector v, and multiply by these deltas, it gives you the change in v in going around a small loop. So it's a very concise trick to compute how a vector changes when you go around a small infinitesimal loop, which is made up out of a pair of vectors, delta and d, delta x and dx. Okay, quite an elegant expression. And now all we have to do is plug in the definition of the covariant derivatives, work out the commutator, and what is the object that we will have constructed, incidentally? The curvature tensor, because it's the curvature tensor that tells you what happens when you go around a little loop. Okay, so let's write them down. We're interested, let's write out the expression. Yeah. Okay, so let's writing it out explicitly. It's d nu plus gamma nu. That's del nu. I bring you over to here again. Del mu is just derivative plus multiplication by gamma. And remember, gamma is a matrix, or a set of matrices. D nu plus gamma nu, that's delta nu. And then d mu plus gamma mu. That's the product, delta nu on the left and delta mu on the right. Now we have to switch them and subtract. Minus d mu plus gamma mu times d nu plus gamma nu. And then multiply it by the vector v, but for the moment I'm only interested in writing the operators down. Okay, so let's work it out. The first term that I get contains no gammas. It's just delta nu times delta mu minus delta mu, oh sorry, not delta. It's just derivative with respect to x nu, derivative with respect to x mu, minus derivative with respect to x mu, derivative with respect to x nu. Is everybody comfortable with my writing expressions like derivative with respect to x mu is just d mu? Okay, I think I've done that before. But d sub mu just means derivative with respect to x mu. All right, so the first term is just gotten by d nu times d mu, sorry, d delta derivative. Derivative nu, derivative mu minus derivative mu, derivative nu. What is this? That's zero. Ordinary derivatives commute with each other. Ordinary derivatives, it doesn't matter the order of differentiation. So the first term is zero. Okay? The term just involving derivatives. Next, we get gamma nu times d mu. But then we have another one over here which is almost identical except in the opposite order. D mu times gamma nu. So that's minus d nu, sorry, d mu, times gamma nu. Okay, d nu, no, yes, no, no, yes. Gamma nu times d mu, that's here. And then d mu gamma nu, that's here. What is this? This is just a commutator of gamma mu with d mu. Right. We can write this as, I guess it's minus the commutator of d mu with gamma nu. Gamma nu is a function of x. D mu is just derivative. What is this commutator? Okay, now you have to go back and remember. Yeah. There it is. There it is. Derivative times f minus f times derivative. That's exactly what we have here. And I hope I have the sign right. This should then be minus the derivative of gamma nu with respect to x mu. It's just a function, but it's the function that's made by differentiating gamma. Okay? That's the, I get that term. Let's see, which ones have I taken care of? We've taken care of this product and that product. Now we've gotten gamma nu times d mu, that's this, and d mu times gamma nu. Now, there's another term in here. All right, let's collect this term. There's another term in which mu and nu are interchanged. In which mu and nu are interchanged. And it comes in with the opposite sign. That one is going to be plus d nu gamma mu. And that's equal to plus d by dx nu gamma mu. You can hunt around in here for those terms. One of them is easy to find. Let's see. Derivative with respect to, here it is. Derivative with respect to x mu times, no. Derivative with respect to x nu, that's here, times gamma mu. That's this one. Comes in with the opposite sign. Looks the same, except mu and nu are interchanged, then you have the opposite sign.
Question.
Okay, yes.
You have the derivative of gamma nu partial x nu. Gamma nu, what is that? I mean, that's a matrix, right?
It is a matrix.
So what's its derivative with respect to x nu? I mean, what
But it's a matrix which depends on position. So it means you differentiate each component of the matrix. Yeah, yeah. It just means you go through the matrix differentiating its components. Right. Okay, so that's easy. And yes, please keep in mind that there are matrix entries here which I've purged out of the formulas. And now what's the last term? The last term is gamma nu times gamma mu minus gamma mu times gamma nu. Right? So the last term, I'll write it in here, is plus gamma nu gamma mu minus gamma mu gamma nu. Now, why isn't that 0? Why isn't gamma nu times gamma mu equal minus gamma mu gamma nu equal to 0? Because they're matrices. Right. Okay, so let's collect it all together and put back the matrix indices, and we will have an expression for the curvature. We'll have an expression for the small change when you go around a closed loop. So let's see. We first have d nu gamma mu. I'll put in the indices in a minute. I just want to write it out. Minus d mu gamma nu plus gamma nu gamma mu minus gamma mu gamma nu. Okay, let's put back the matrix entries now. I'll do that in red. Oh, alpha, beta, alpha, beta. But here we have matrix multiplication. We want the alpha beta'th element of the matrix gamma times gamma. So that becomes alpha delta delta beta. That's multiplying the matrix gamma alpha delta by the matrix gamma delta beta. Einstein summation convention, sum over delta. That's a simple way to do matrix multiplication. And same thing over here, alpha delta delta beta. That's the, and what's the whole thing? The whole thing is the curvature tensor. But what do we do with it? What we do with it is we multiply it. First of all, we multiply it by delta x nu and dx mu. Delta x nu dx mu, that's our little rectangle, or the sides of our little rectangle. And then we multiply it by v beta. And what does it give us? It gives us the change in v alpha. The only open index here is alpha, I hope. Nu and mu have been soaked up. Alpha, beta, yeah. It gives us the change in v alpha when we go around the closed loop. Well, the change is a very small change if you go around the small loop. I've drawn it as a big change. But that's the change, and notice that it contains the edge sizes quadratically, so it's proportional to some area in there. It contains v itself, so it's some operator acting on v, and it contains this big structure, this big ugly structure here called the Riemann tensor.
The v on the right-hand side of the top line.
I'm sorry. Yep. Right. All right. So this is the Riemann tensor, R nu mu alpha beta. And I think in my notes last time I may have had an index misplaced. That's the Riemann tensor, and it is d nu gamma mu alpha beta minus, oh yeah. Okay, I'm gonna do it this way. Plus gamma nu alpha delta gamma mu delta beta minus what happens is if you interchange mu and nu. I'm not going to write the whole thing out. It contains one term with a mu and a mu, and the other term is identical except just interchange nu and mu. And not surprising, since after all we were taking a commutator of something that we get minus signs in it. That's the Riemann tensor. And we could plug it into this formula over here, and we see that the Riemann tensor is the construction for telling you how to change a vector when you go around a little closed loop. Questions? Yes?
It looks like you picked kind of a plane.
Say it?
It looks like you picked kind of a plane.
I picked a plane. I picked a plane to go around.
So it doesn't matter, that choice doesn't.
Yeah, but right, once I know the general formula, I can choose that plane any way I like by choosing delta x mu and delta x nu to be arbitrary little vectors. In other words, any plane that can be characterized by two vectors. Any two vectors characterize a plane. So if I choose two vectors, two infinitesimal vectors, delta x nu and dx mu, these are two different vectors, delta and d, then they define a plane. And that's right, what we're doing is we're picking out a plane, taking a small little loop in that plane, going around that small little loop, and seeing what happens when we covariantly transport a vector And the result is that when you go around, it will reorient itself
I
in some
guess
new
another
direction.
way of answering that question
Was there a question?
is that mu and nu are free indices, so that really is not one.
Oh, yes, yes. They're not free indices in this final formula here. Before I contract them with this little area element, they're free indices. But when I decide what...
Yeah,
Yeah.
I'm just saying that you can, well, what,
You get the same Riemann tensor no matter what plane you pick.
Yes, you use the same Riemann tensor, but you use different components of it when you choose different planes. Right.
I'm trying to understand what happens when delta xn and delta x nu and dx nu go to 0. What else goes to 0 then? To give me a limit.
0 in length, for example. Yeah, the change in the vector goes to 0. The change in the vector, if you go around a small loop, as the loop gets smaller and smaller, let's say we take this vector and we go around, the smaller we make this loop, the smaller the difference between the vector when we go around. But we want to keep track of that small distance, that small difference. We could, for example, choose a bigger circle and integrate up the effects of small little bits of curvature. We want to keep track of that little difference.
But nothing in the Riemann tensor looks to me like it depends on the size of that circle.
Nothing in the Riemann tensor depends on it. This is what depends on it.
Yeah.
This does.
Okay, but I want something else to go to 0. I want something else to go to 0, so the rest of it has a...
The answer goes to 0.
Okay.
Right.
Okay.
okay, let me change what I was
Yeah,
saying.
let's, I can see why you might have gotten confused. Let's put this up here, equals delta V alpha.
Now I'm happy.
Right.
Thank you.
Right. Good. Now notice, this quantity is quadratic in small deviations here. So it's doubly small, so to speak.
But we're adding up all of the curvature components of each of the planes for
Right.
each of the basis vectors.
Well, supposing I arbitrarily said, let's take delta x nu here to lie along the x-axis.
No, I'm just saying, because we're contracting those,
Yes.
we're adding up all
Absolutely.
of the components in all of the different directions.
Right. Right, that's right. Okay, so that's the Riemann tensor. If you now use, now I don't know any, well, I know some simple ways to see some of the symmetries of this. Incidentally, it is a tensor. It's made up out of covariant derivatives of covariant derivatives, and covariant derivatives are the things which make tensors. So it is guaranteed to be a tensor. Since it's a tensor, I can lower the index alpha if I like and put all the indices downstairs. I can do that if I like. And we just lower the index. How do we lower indices? Yeah, by multiplying by the metric, or the appropriate way. And so we can also write R nu mu alpha beta. It's a different thing, has different values, but we can get it directly from here. All right? It has antisymmetric indices nu and mu. It's clearly antisymmetric under nu mu interchange. If you interchange nu and mu, we interchange a term from here with a term from here. So it's antisymmetric if you interchange nu and mu, keeping alpha and beta fixed. It also happens to be antisymmetric. This is something you can check by direct calculation. It's also antisymmetric if you interchange alpha and beta. Okay. You can prove this in a number of ways, which I'm not going to do, but one of the ways is by simply demanding that the vector as it's transported around doesn't change its length. That's enough to prove that it's antisymmetric with alpha and beta. I'm not going to prove that. We've done as much mathematics as I want to do tonight. So let me just indicate that by putting a little arrow here and a minus sign. That means that if you interchange mu and nu, the sign of the Riemann tensor changes. It's also antisymmetric with respect to alpha and beta. And it has the further property that if I literally pick up mu and nu and interchange them with alpha and beta, it's symmetric. So I'll indicate that by some sort of plus sign like that. What this plus sign means is that this is the same, or it's equal to R alpha beta mu nu. No, nu mu. Nu mu. If I take alpha and beta and interchange them with nu and mu, the pair of them, then nothing changes. If I interchange a nu and a mu without changing an alpha and beta, it changes sign. And if I interchange an alpha and beta without interchanging mu and nu, it changes sign. So those are the basic properties of the Riemann tensor. Probably. Probably. Almost undoubtedly. Everything you want to know about it, though, you can find out by plugging in for the gammas their expression in terms of derivatives of the g's. So let's see what it is. Okay, let's just get a rough idea. What kind of things does a gamma have in it? The gammas have in them first derivatives of the metric. Okay. Also has inverse metrics, but it contains, as far as derivatives go, each gamma is proportional to a single derivative of a g. I'll write them out later, but let's just keep in mind. That means that these terms here contain second derivatives of g. So the r's have second derivatives of g, of the metric, and these terms here are quadratic in first derivatives. The gamma contains a first derivative. A gamma times another gamma contains a first derivative times another first derivative. So the r's contain two kinds of terms, one of them being quadratic in first derivatives, and the other kind being second derivative of a g. Second derivatives of g and quadratic in first derivatives of g. They always contain two derivatives. Sometimes the two derivatives act on one g, giving you second derivatives. Sometimes it'll be a product of a derivative of g times another derivative of g. And that's the character of the Riemann tensor. It is quadratic in derivatives, made up out of the Christoffel symbols. Christoffel symbols are themselves made up out of the metric. So if you know the metric tensor as a function of position, with a great deal of labor and effort, you can work out all, I think it's 24 components, independent components of the Riemann tensor. It's only 6 in 3 dimensions and 1 in two dimensions.
Question?
Yeah.
It keeps waiting for you to divide both sides of that long line by dx mu and get a mixed partial on the right-hand side?
Well, I think this is the way to express it. I know you're waiting for me to do that, but I don't think it's appropriate to do it. It's not a second derivative of anything. It is what it is. All right, now, as I said, the basic idea is simple enough. The equations are rather complicated and not terribly pretty. They can be simplified. I don't think I ever wrote. We can also write in a very simple form. We can just write that R nu mu alpha beta, thought of as a matrix. R thought of as a matrix, so let's suppress its matrix indices, is just the commutator of two covariant derivatives, nu and mu. That's the most elegant way to write the Riemann tensor, and to remember that each one of the objects in there is itself a matrix. Whatever, alpha beta. All right, that's an elegant representation for it. But when you actually come to calculate, this is the thing that you are calculating when you calculate the Riemann tensor. Now, there are some other tensors that you can make up out of the Riemann tensor. The Ricci tensor and the scalar curvature. I'll define them now. They play a very important role in general relativity. No. This is a thing with 4 indices, but I've suppressed 2 of the indices, and it's antisymmetric under mu and nu. Okay, so it's definitely not the Ricci tensor. The Ricci tensor, now I could try contracting, all right, let's see what we can do. Let's see what we can make up. Let's take R mu nu alpha beta. In fact, let's take it in that form. Can I contract mu with nu? How would I do that? I would multiply it by g mu nu, and that would give me a thing with just an alpha beta index. This is 0. Does anybody know why this is 0? Because R is antisymmetric and G is symmetric. Whenever you take a symmetric matrix and contract it with an antisymmetric matrix, you'll always get 0. You'll get as many positive terms as negative terms, and so you'll always get 0. So you can't contract the mu and nu and get anything interesting. Same thing with the alpha beta. Remember that this matrix is also, when everybody is written with lower indices, it's also antisymmetric with respect to alpha and beta. So contracting alpha and beta will also lead to grief. You'll get nothing. But if you contract alpha with nu, for example, meaning to say you multiply the whole thing, well, what does it mean? It means you just write R mu alpha alpha beta and contract and sum over the alphas. That gives you a non-zero thing, which is called the Ricci tensor, and it's R mu beta. All right, it exists. It's not 0. And how many components does it? It's also symmetric. The reason it's symmetric is some of the symmetries of the Riemann tensor. It's not hard to show. You know enough. I've told you enough to prove that it's symmetric when you interchange mu and beta. That is, where is it? If I bring this alpha downstairs, alpha beta, then it's the symmetry under interchanging these two. The result is that R mu beta is symmetric. It's equal to R beta mu.
Say again how you contract the Riemann tensor.
This one and that one. There's no ambiguity, really, apart from a sign. If you choose the wrong two to contract, you'll get 0 by antisymmetry. If you pick the right one, they're all the same. There's enough symmetry to make sure the answer is always the same.
What would you do? You multiply that by delta?
Well, if I put the alpha, let's see, if I...
No, I mean, when you change do the substitution, isn't that the same as Kronecker delta?
Kronecker, yeah.
It's like Kronecker delta alpha nu.
That's right. Or we could put the alpha index downstairs and then just multiply by G nu alpha. In other words, we've got to contract these two indices, nu and alpha. We can do it in any number of ways, all the same thing. And you get a tensor with 2 indices. Take any tensor with 4 indices, and by contracting the indices, identifying an upper with a lower, and then summing, you remove those 2 indices and you get something with 2 fewer indices. So that's R beta mu, and that's Ricci. This is Riemann. Okay? There's one last tensor that you can make. And the last tensor,
Is there some way to differentiate the two different R's when you write them?
Ricci and Riemann,
Yeah,
you have to put a number of indices.
you just have to, okay.
Yeah. They're both called R, unfortunately. And then there's one more thing that's called R. It's the Ricci scalar. The Ricci scalar is just gotten by taking, the curvature scalar. Sorry, the curvature scalar is just gotten by taking the Ricci tensor and contracting its two indices, which you do by writing R beta mu G beta mu. And that's just called R. And it's just called the curvature scalar. If the curvature scalar is not 0, the space is curved. But if the curvature scalar is 0, it doesn't mean that the space is not curved. Any component of the curvature, if it's not 0, the space is not flat. But you can have situations where the curvature scalar is 0, even though the components of either the Ricci or the Riemann tensor are not. So the vanishing, well, okay, let me put it this way. The vanishing of the curvature scalar is necessary for a space to be flat, but it's not, and when I say vanishing, I mean vanishing everywhere. I mean vanishing as a function. If it vanishes, that doesn't mean the space is flat, but if it doesn't vanish, it means the space, did I say this right? It is necessary for flatness, but not sufficient, except in 2 dimensions. In 2 dimensions, there is only one independent component of the Riemann tensor, easy to prove, and it can be rewritten in terms of the scalar curvature. So in 2 dimensions, it's both necessary and sufficient for a space to be flat, for the Riemann or for the curvature scalar to be everywhere 0. Yeah.
An example of that would be a saddle point, a saddle point of a saddle shape.
Well, it would not be 0 there.
Yeah, not be 0.
No.
The scalar would not be 0.
No, scalar curvature would not. Okay. In 3 dimensions, it's necessary and sufficient for the Ricci tensor to be 0 in order to have a flat space-time. But in higher than 3 dimensions, neither the scalar nor the Ricci tensor by itself completely determine whether the space is flat. In principle, you have to check every single one of the independent components of the Riemann tensor to determine whether a space is flat. But if all the components of the Riemann tensor are everywhere 0, the space is flat. Now, I haven't proved that, but that is a theorem. That is a theorem.
So in a great circle, in other words, in a great circle on a sphere, you would have flat space.
No.
That's only, no, remember, the Riemann curvature, or any of these curvatures, has to do with small little loops. What happens when you go around small little loops? In other words, the statement is, if the Riemann tensor is, if the scalar curvature is 0, then any little loop that you go around, the vector will come back to itself.
I think he's confusing it with the geodesic.
Yeah,
And actually, if you go around the Arctic Circle, that is not a geodesic.
No, oh no, definitely not. That's right. If you go around the Arctic Circle at 10 degrees around the Arctic Circle, that is not a geodesic. I'm not sure if that's what the confusion was or not. That is not a geodesic. It's great circles which are geodesics. Okay, so now we know a great deal about what curvature is. Keep in mind that curvature does not have to do with the way the thing is embedded in space. I mean, for example, this piece of paper has 0 curvature whether you do this to it, that to it, this to it, that to it, or any other kind of bending that you can do to it. The intrinsic properties of the space, the properties that are felt by that tiny little bug that can only walk on the space and can only feel his way around on the space itself, those properties don't depend on the way that it's embedded in a higher dimensional space. The properties of how it's embedded are called extrinsic properties. So if I press this down on here, it has 0 intrinsic curvature. It also has 0 extrinsic curvature. If I bend it up like that, it now has 0 intrinsic curvature, but non-zero extrinsic curvature. So don't confuse those two concepts. And at the moment, we're only interested in intrinsic properties of the space, what we can feel moving in our own space-time. Okay, so that, I think, is curvature. Now I want to come to motion of particles, slow particles in particular. What we want to do, I'll tell you right now, the Riemann tensor, of course, and its various friends here are the gravitational field. And we're going to want to find the approximate connection between these things and the easier to think about Newtonian approximation. How are these objects connected to the things that Newton would have understood as the gravitational field? I don't think Newton ever really defined the field concept, but we could have easily explained it to him as the field of acceleration. As we move around in space with a point mass and see what its acceleration is, that acceleration defines a vector field every point in space, and that's what we would call the gravitational field. And the question is, how is it connected to these much, much more complicated objects here? All right, the first step is to understand acceleration along geodesics, what the idea of acceleration along geodesics. Now, a geodesic is the straightest possible path. The straightest possible path in space-time, if there's no curvature, is, of course, a straight line. Straight line means unaccelerated uniform motion, no acceleration. But in curved space-time, is just no concept which is quite equivalent to a perfect straight line. And no matter what we do, we will find the concept of acceleration in a curved space-time. And that's what gets related to the Newton force law. Okay, but let's go back now. I think we did a bit of this last time, but I want to go through it more carefully now. I want to talk only now about things which are moving slowly. We're going to restrict ourselves for a little bit to things which are moving slowly. And furthermore, they're moving slowly in a gravitational field which is not so strong that the Newtonian approximation breaks down. Can you think of a gravitational field where the Newtonian approximation really breaks down badly? Sure, a black hole. Or the expansion of the universe or whatever. So if we're thinking about the kinds of gravitational fields which are made up out of planets and stars and so forth, for which the Newtonian approximation is good, then general relativity should reduce to Newtonian physics. We should have an F equals ma, and we should have a force law, which we recognize as Newton. So let's first begin with the F equals ma idea. And let's just think about the acceleration of a particle moving on a geodesic. The rule of general relativity is very simple. Particles move along geodesics in space-time. It's a marvelously simple rule, a lot simpler than anything Newton could have said. They just go as straight ahead as they can in space-time. All right, what's the equation for that? Here's the equation for a geodesic. It's just that the tangent vector is covariantly constant along the trajectory. It's just d second x by d tau squared x mu. Tau is proper time along the trajectory. D tau squared is equal to g mu nu dx mu dx nu. That's d tau squared. Take its square root, and it becomes d tau. It's along a trajectory, and the second derivative of x with respect to tau squared plus gamma, let's see, what do I have here? Sigma lambda mu dx sigma by d tau dx lambda by d tau. This is the covariant derivative of the tangent vector. Remember what the tangent vector is. The tangent vector is the vector whose components are dx mu by d tau. That's the tangent vector. All right. Then we take the tangent vector and covariantly differentiate it along the trajectory itself. If this is equal to 0, everywhere is along the trajectory, then the trajectory is a geodesic. Or another way of saying it is this becomes the equation of motion for a particle moving in a gravitational field or moving in a space-time metric. All right, now let's imagine a frame of reference. Let's suppose there's a frame of reference in which everything that we're interested in is moving slowly by comparison with the speed of light. And everything is changing in time slowly. Nothing is very, very rapidly changing in time. That's the condition for Newton to be approximately correct. All right, first of all, what's the connection? If a trajectory is moving slowly, that means in some frame of reference it's moving practically vertically. What is the connection then? What's the connection then between tau along the trajectory and ordinary time? Okay, there's an assumption involved there, and I'll tell you what the assumption is. The assumption that's involved is that g mu nu is almost equal to delta mu nu. Is almost equal to eta mu nu. Remember what eta mu nu is? It's the metric of special relativity. Right? So there are two assumptions. One is that there is a frame of reference in which everything is moving slowly and everything is changing slowly. And we'll work in that frame of reference. And the other is that the gravitational field is weak. To say that the gravitational field is weak is to say that g mu nu is equal to eta mu nu plus a small correction. That the correction to flat space-time is small. Okay. Let's make that assumption. Now, with that assumption, things moving slowly, and the metric approximately of the Minkowski kind, then it is true that x naught, which can also be called t, is the same as tau along a trajectory. Again, I've set c equal to 1, so you can put back the c's. They're worth putting back. All right. But that in particular says that the x naught by d tau is equal to 1 plus tiny, tiny corrections. Corrections which are small when things are moving slowly as compared to the speed of light. And if the x by d tau is always equal to 1, if the x naught by d tau is always equal to 1, then the second derivative of x naught with respect to tau squared is always going to be very small. So we don't have to worry about that. That's not something we have to worry about, the time component of x. It's the space components of x that we want to deal with. All right, so once we say that tau is close to t, to within very small quantities, we could pick out one spatial component of x. Which one should we pick out? Let's just pick out x. X itself, x as in x, y, and z. Let's pick out x. d second x by d tau squared is the same as d second x by dt squared, also known as the x component of acceleration. All right, so the first thing is, in a frame in which everything is moving slowly, and in which the gravitational field is practically is small. Small means close to the standard Minkowski metric. In that case, this term in the equation is nothing but ordinary acceleration. In this case, along the x-axis, a similar one for y and z. Plus, now what appears here, since this is acceleration, what appears here must be associated with gravitational force. We might want to multiply by m, but we don't, let's not bother. Here's the acceleration, and so it's related by a factor of m to the force, but let's look at it for a minute. dx by d tau, if we pick out a space component of x, dx by d tau is small, very small. Why is it small? Because by assumption, we're working in a frame of reference where everybody is moving very slowly. Moving slowly means dx by d tau is small, dy by d tau is small, and dz by d tau is small. The only components of the 4 velocity which are large, there's only one component of the 4 velocity which is large, and that's dx naught by d tau. How big is dx naught by d tau? 1. So to a good approximation, the only thing which is here is gamma 0, 0, mu dx naught by d tau, but that's just 1 dx naught by d tau.
There is no mu.
Hmm?
There is no mu.
There is no mu?
There is 0. Would be 1.
Yeah, good. I was just about to do that, right. Yeah. Anyway, these are 1, and now this is just x, or 1, depending on how you like your notation. X is the first component of x, y, and z, so this can either be 1 or x. So what have we found out? We found out that apart from a minus sign, equals minus, that this is the field of acceleration. The Christoffel symbol, but in particular the Christoffel symbol with 2 zeros downstairs and an x upstairs, is the x component of acceleration with a minus sign in there. Let's write that out. Let's write it out, taking into account some approximations. First of all, what is this gamma x0, 0? We're going to assume now that g mu nu is equal to eta mu nu plus small correction. That also means that g super mu nu is eta super mu nu, which is the same symbol, plus small corrections. Okay, so let's write out what this gamma symbol is. It's equal to gxx with upstairs x's, 1/2 times the derivative of g x0 with respect to x naught plus the derivative of g x0x with respect to x naught minus the derivative of g naught naught with respect to x. All right. That's basically what it is. What I'm doing is I'm using for g out here just eta. Why don't I keep the corrections, the small, all right. I'm not going to keep the small corrections to g in this expression out here. Why not? Because it's second order. Obviously, this is proportional to the corrections. If there are small corrections, this will be proportional to the corrections. Why? because when you differentiate g, you get nothing from the big term in g, and you only get contributions from the small term. So this here is already first order in small things. All right? If I want to keep only things which are first order in small things, I don't want to write the corrections to g here. This just becomes eta, this just becomes eta xx. And what is eta xx, the xx component? You fail. Who was it? You get a D. What is eta xx? -1. Remember, it's dt squared minus dx squared. Right. So we got to keep our signs correct. I'm going to lose the sign. I'm sure I'll lose the sign. Let's see. This is, since I've got a minus here, I probably want another minus here. But eta xx is minus. I know that my sign is going to come out wrong.
It doesn't really matter which you use, as long, because you're going to get a GTT over there. So.
Yeah, no, it doesn't. In that sense, it doesn't matter. Well, no, it does. Well, let's be careful and be consistent. Eta xx is -1. So let's see. I've lost the thread. I don't remember how many times I've changed the minus sign.
Okay, you started with a minus sign from the original equation.
Yeah.
Okay.
So that's this minus sign
then
here.
Then you have a minus sign for the Christopherson. There's a leading minus sign there.
From the eta?
Does Christopherson symbol give you -1/2 or +1/2?
No, I think it's +1/2.
Oh yeah, it's +1/2.
Yeah, but this is minus.
You get a minus because you got the third term, and two of those terms go away.
Right. Right. Now, the reason that these go away, why do these go away? These go away because we're assuming that everything is moving slowly. If everything is moving slowly, it means the components of the gravitational field change slowly. If the sources of the gravitational field are moving slowly, for example, the sun is at rest in our frame. If the sun is at rest in our frame, then the components of the metric don't change with time. None of the components of the metric will change rapidly with time if everything is moving very slowly. So in the Newtonian approximation, the time dependence here is very small, and we can neglect this. The only big term is this one, and so altogether then we get an equation that the second derivative of x with respect to t squared is equal to 1/2, with a minus sign it looks like to me, the derivative of g naught naught with respect to x. What would you have written in Newtonian gravity? Let's go back to Newtonian gravity now. You would have written
GM1 over.
Well, let's not worry about the detailed form of the gravitational field, but yeah, the force is a gradient, or the acceleration is the gradient of the potential, right? So we would have written in Newtonian physics the second derivative of x with respect to t squared is equal to minus, I think, the derivative of the potential, let's call it phi, with respect to x. And basically the same kind of formula. I have a feeling I have a sign that I've lost, that I've dropped a sign.
GXX is negative. And you also have a negative sign.
Where did I drop the sign? Should this be?
Where it says gamma 00x equals 1/2, there's supposed to be a GXX there, which is negative.
I have a feeling I've lost a sign. Let me just see. Yeah, I thought I kept track of it, but now it looks It's too late and I'm too tired to go through the signs carefully, so, well, of course it is important, but at this point it's not so important. It is important, but we'll have to come back to it. I'll get this. It's either right or it's wrong. I have a 50% chance of gravity being attractive or repulsive. That's the point. Okay. Get the wrong sign there, and you'll find that gravity is repulsive instead of attractive. All right. So it appears then that to within a sign, there is a close connection between the gravitational potential and G naught naught. Now, I thought that, all right, the way it's written, it says that G naught naught in this approximation should be equal to phi, but does it say that? Not quite. Why not? Plus a constant, right? Plus a constant. Plus a constant. And a factor of 2. Good. The factor of 2 goes over here? Yeah. So G naught naught, the time component of the metric, incidentally, very far from a gravitating object, the metric should just go over to the standard Minkowski form without any gravity. In that case, the C would just be 1. We'll come back to it. We'll come back to what this constant is. It's really just 1. But we will come back to it. Okay, so in some way, G naught naught is related to twice the gravitational potential. Keep that in mind. We're not going to write down today the theory of a concentrated mass, but that will come up. We've now learned something about the metric tensor. We've learned that if we know what the Newtonian potential is, then we have an approximation to a piece of the metric tensor. That's information. And it's information that we'll use in trying to build the Einstein theory. Okay, now let's keep that in mind, and let's go back to Newton, or let's continue with Newton, and say, what do we know about this quantity phi? Well, phi is the thing whose gradient is the field of acceleration. Earlier in the course, what I called A, the acceleration field, is minus or plus. And now I've lost track. Again, I'm going to have trouble with signs tonight. I think it's just the derivative of phi. That's like force is minus the derivative of phi with respect to x. I think that's right. Definition. All right, now how is phi connected to the sources of the gravitational field? Here's where we're going now. We know that phi is connected to the metric in a certain way, which I've raised up out of sight. Phi is connected to the metric, or is essentially a piece of the metric. On the other hand, phi is related to the sources of the gravitational field, which are mass. Well, that's going to tell us that the metric itself is somehow controlled by masses. So what's the connection between phi and mass density? Let's call mass density rho. Rho is mass per unit volume. Okay? Let me remind you that the connection between A and rho is that the divergence of A is equal to, now is that correct? No. There's a factor of G. What else? 4 pi. And a minus sign if I'm not mistaken. All right. Now, this tells us since A is the gradient of phi, and this is the divergence of A, this can be written as del squared phi, or maybe with a minus sign, is equal to 4 pi rho g, where del squared of phi means the second derivative of phi with respect to x plus the second derivative of phi with respect to y plus the second derivative of phi with respect to z equals del squared phi. So here we have an equation which is some simplified approximation to an equation which connects the metric to the mass density. Now, mass density, of course, is the same as energy density. E equals mc squared, and c is equal to 1 in our units. And so the right-hand side is really 4 pi g times the energy density. Well, the last time we talked about energy density and momentum density, and we put them together into a big matrix, and the matrix was called the energy momentum tensor. Okay. T naught naught. What was T naught naught? Energy density. What was T naught 1? Energy flux or energy flow. How about T1 naught? Momentum density. All right. On the right-hand side, it's pretty clear that what we have is T naught naught, the energy density, which is the same as the mass density. So we have an equation which has the form del squared phi is 4 pi g times T naught naught, roughly speaking. But what is on the left-hand side? On the left-hand side is the second derivative of phi, which is closely related to the second derivative of g naught naught. Remember, what was the connection now? Phi is equal to either 1/2 g naught naught or twice g naught naught. Which way was it? Phi is equal to 1/2 g naught naught. So on the left-hand side, I can write that this is 1/2 del squared, second derivative of g naught naught. These are spatial derivatives, two spatial derivatives on g naught naught, and that's equal to 4 pi, I'm going to write 8 pi g t naught naught and get rid of the half here. Okay. We're starting to get some geometric picture of how gravity works, that the energy momentum tensor, its naught naught component, somehow determines g naught naught. But what's wrong with this equation? Is this a sensible equation? Well, it's an okay equation, but the problem with it is that it's not a tensor equation. It's not written explicitly as a tensor equation. It's not clear that we've derived it in a particular frame of reference, a frame of reference where everything is moving slowly. Unless we can express it as a tensor equation, we will not expect it to be true in an arbitrary frame of reference. The whole point of tensors is to write equations which are the same in every reference frame. And while the right-hand side is indeed a component of a tensor, tensor equations incidentally mean whole tensors, all their components are equal to other tensors, not just that the naught naught component of a tensor is equal to some other naught naught component. First of all, I don't like this because it has two indices downstairs and one index upstairs and two indices upstairs. That's really not the problem with this. We could lower both these indices and not worry about that. But the problem is it's just not a tensor equation as it stands. Is there a tensor equation which, in the limit that we're talking about, everything moving slowly, weak gravitational fields, is there a tensor equation which becomes equal to this? Well, on the right-hand side, we have a piece of a tensor. we should be looking for some kind of equation which looks something like this. A tensor on the left-hand side made up only out of the components of the metric. Let's give it a name. Let's call it G mu nu. I don't know what it is yet. I know some things about it, but I don't know what it is yet. But it's something made up only out of the metric and some of its derivatives. And on the right-hand side, 8 pi g t mu nu. Supposing I was able to find a tensor which had the property that in the frame where everything is moving slowly, its naught-naught component simply reduced to this. Then my guess would be that the full gravitational theory in frames of and other frames of reference, or in situations where things are varying rapidly, in situations where the approximations are not quite so good, this would become the full theory. So the question is, what is this? Well, let's see what it has. It's made up out of the metric, and it's made up out of second derivatives of the metric. What tensors, oh, and it also has to be a tensor with only two indices. Why two indices? Because it's going to be equal to some tensor on the right-hand side with two indices. The energy density is a piece of a tensor with two indices. The left-hand side has to have two indices, made up only out of the metric and only having second derivatives or containing second derivatives of the metric. Any suggestions by now before I might go there? Yeah, R mu nu. But there's another tensor that we can make with two indices that also is made up out of the same kind of things. And I'll tell you what it is. Yeah. R, the scalar R, times G mu nu. A scalar, remember, that's this is this curvature scalar, the scalar curvature. Everybody's been contracted, times the metric itself. So there are two tensors which could go here, and some combination of them, some coefficient, let's call it a numerical coefficient. And when I by numerical now, I mean like it could be 3, or it could be 1, or it could be 7, or whatever, plus some other numerical coefficient b times delta mu nu times r. And that's it. There are no other tensors which contain only the second derivatives and which are made up only out of the metric other than a times r mu nu plus b times delta mu nu r. That's equal to 8 pi g times t mu nu. So, g mu nu, sorry. G mu nu. Right, left-hand side is a tensor, the right-hand side is a tensor. If they're the same in one frame, they're the same in all frames. So all we have to do is search for some numerical coefficients a and b so that the left-hand side in the limit of everybody moving slowly is just del squared of g naught naught. We're not going to do that tonight. There is a solution to that. If there wasn't, we wouldn't be here. It's called capital G mu nu. And it's also called the Einstein tensor. All right? But that's the goal. So the logic has been pretty clear. We've decided to look at the theory in frames of reference where everything is recognizably small and Newtonian, came to the conclusion that our equations are going to be something like this. How did we find out that G mu nu was, or that G naught naught was related to the gravitational potential? By studying the theory of geodesics. All right, by studying the theory of geodesics, we found that G naught naught was essentially the same as phi with a factor of 2. Or the derivatives of G naught naught are the same as the derivatives of phi. And this equation represents nothing but del squared phi is 4 pi g rho. and then looked for a generalization of this which has the form of a tensor equation. So far, I haven't told you what is here, but it's more or less obvious that it should have something to do with the curvature tensor simply because it's got to be made up out of a thing with two derivatives acting on the metric tensor. Okay, the next time we will explore what A and B are, what the principles are which govern A and B, and what the numbers are. I'll tell you right now, the numbers are 1.5. 1 and plus a half, 1 and minus a half, minus a half. Yeah, yeah. So they're real easy numbers, and all we really have to show. Well, we have to show a little more than that, but that's the basic set of ideas, and that's general relativity. So it's not so hard, is it?
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.